Hello everyone. Let's get started. In our last video, we discussed spectral decomposition theorem. The spectral decomposition theorem, it's very important because we will study something called deformation gradient. By using the spectral decomposition theorem, we can define the deformation gradient in principal axis configuration. Then our constitutive model, the equations uh, will be more concise and easy to handle, right? Most of the complicated problem, simply you can develop the constitutive model by using the spectral decomposition theorem. I have used a lot because, but I see most of the people, they don't use this one, but I have used a lot. I experience many applications of this spectral decomposition theorem in my case. Okay, as I told in our previous video, uh, we are going to start the fundamental of uh, continuum mechanics soon. So before that, we have to complete one of the important parts called derivative and divergence, right? We are going to start that one very soon. Uh, so my initial plan was discussing those things in this video. So before starting that, so let me discuss one of the another important concept in mathematics called Taylor series, right? This Taylor series it's very fundamental, especially for calculus, and also it is the very fundamental for finite element techniques, right? Something we studied in finite element. The Taylor series is very important stuff, important things we are going to study. Okay, right. In the finite element series, I'm not going to discuss the derivation of the finite element series here. We can derive that one from the power series. uh, I, I'm not going to discuss the derivation here because it's not going to help us. uh, we because we are going to we don't use that derivation in our continuum mechanics, right? So in Taylor series, actually, the generalized version of Taylor series, you can write it for any uh, dimension function, right? So for that, let's understand what is the one variable function first. Okay, so here, so what I'm going to explain in this video, actual physical meanings of the finite, that means Taylor series, right? So for that, let me take this picture. This is I have taken from the Wikipedia. The graph shown in the black color, it is actually our objective function, or we can say the function developed using infinite number of terms, infinite in Taylor series, right? So for the time being, let me say this is objective function. So that means this is the actual function. Let's see, we don't know the equation of this function. Okay, so what we are going to do, we are going to approximate this function using Taylor series, right? So before that, let me write the expression of the for Taylor series. The Taylor series expression f of x equal, uh, we consider the infinite number of terms n equals 0 to infinity. Uh, this is nth derivative of a function at one point. I will tell you what is the meaning of a here, over n factorial into x minus a to the power n. So this is the Taylor series expression for one dimension case. So here, some of the important things you have to understand. The first one, A. A is the point where we do the approximation, right? I can write it like this, right? At point, okay, where we do approximation, right? For example, in this case, let me take a different color. Okay. Right. So in this case, in the picture, they have taken the approximation at the initial point, the origin. That means a equals 0 here in this particular picture, right? If someone want to do the approximation for this objective function, so he can do it from here also. So here, what is that? A equal 3, 3.2 something, right? Okay, so in that case, a equal 3.2. But here, a is equal 0, right? In this picture, right? Objective function, right? I missed the e. Okay, right. Initially, they have done approximation. Let's say the linear approximation. For this linear, you need two terms, right? The linear equation, a naught plus a1x, right? So this is the linear function, right? So you need two terms. So that means here you consider n equals 0, comma n equal 1. Okay. When you consider these terms, you can develop a linear approximation, right? For example, is this approximation is enough? So what is the meaning of n0 and 1? But for example, if you write it here, let me write the expression in normal way. If we write the expression with normal way, n equals 0, so that means 0 derivative of f. That means no need to do any derivation. Here 0 factorial is 1. So initially 1, right? Okay, because n0 is 1, right? Okay. So that means here you will get this f of a into 1, right? So I can write it f of a, right? F of a. Because 0 means no derivative, f of a into 1, right? The second one, here f of 1, right? First derivative of this one, f of a. So I will write it this one first. Okay. So that means x minus a. Okay. Okay, x minus a, f of a over 1, right? 1 factorial. Then second one, x minus a squared over 2 factorial f second derivative of a, right? So plus third one, f x minus a cube, 3 factorial f of third derivative of this one, right? So like that it will go. In very first case, 0 and 1 mean I am considering only these two terms, right? Okay. So what is the meaning of that? That means this value I know. This is the known value. This point I know the value of the function, right? So I am going to find the value of the function at one point, right? For example, let's say I'm going to find the value at this point, right? I'll use the same color. I'm going to find the value at this point. Let's say 1.x1. I'm going to find the value here. So what is the function value? X1 is. But in this case, I don't know the equation. So how I'm going to do, I can take first two term, then I can find the value. What is that my x here? That is my x1. A is in this case 0. Then I can find f dash x because I know I can find the slope. Just the gradient, right? The slope of that one. So what is that? This is slope. This is x because a equals 0. This is our initial term, right? That is my a naught. This is my f of a. Okay. So what is a1? A1 is my slope, right? X minus a into x. Sorry, this is my slope at a, right? This is my slope at a at this point. This point, the slope gradient. Okay. So then what is x? x is here, x minus a is 0, right? That means x, right? So this is my case, right? In this case, this one is 0, right? Okay. So this is the application of the Taylor series. That means we try to calculate the function value without knowing the equation through the approximation, right? Okay. Right. For example, let's say the second case, right? Second case, let me take this one, right? So here it is not the quadratic term because it is the graph is plus and minus. That means the number of term will be the function, the power of the function will be the odd number, right? So let's say in this case he considered the first four terms, right? That means n equal 3, right? Not n equal 2, right? So he considers 0, 1, 2, 3. So why I am saying 3? Because here third power, right? Because it is odd number because plus and minus here. Similarly, if you increase the number, so here n equals 0, 1, 2, 3, 4, and 5, right? Okay, so till n equal 5 terms he considered, right? Similarly, if you increase the number of term, so here I think n equals 0 to 7, right? Okay. So like that, if we increase the number of term, what is actually doing? We are increasing the approximation range, right? Similarly, in this case, if you want to get exactly the function, you have to consider n from 0 to infinity, right? If we consider infinite number of terms, you can approximate the function till that mean most accurately, right? Okay, how do we decide the number of terms? Again, that is based on our the range, right? For example, if you want to approximate the function within with this range, that linear approximation is more than enough, right? In most of the cases, in our continuum mechanics case, uh, we we deal with the problem infinitesimal problem more closely. So therefore, first uh, first order approximation is enough, right? That means we can ignore the second order approximation most of the cases. Sometimes if we want to use the large train problem, in that case, we can include the second order term as well. Okay, we will discuss those things, right? Okay, so I hope this explanation has given the idea of what is Taylor series here, right? Okay. Uh, Let me take one example, right? So, for example, before that, let me write our finite element series for one dimension case n equals 0 to infinity, nth derivative of function at that point, then n factorial x minus a to the power n. So let's say our function f of x is uh, e to the power x, right? So I'm going to write the Taylor series for e to the power x. So for example here, so let me take the approximation. We'll start with the origin, point of origin. That means a equals 0 here. So then f of nx, first we will consider the nth derivative of x. So n derivative of e to the power x, again the same, right? So from here you can find if a mean here 0. Okay, so that means e to the power 0, it is 1, right? Okay, so therefore your f of x, that means e to the power x now, uh, n equals 0 to infinity. This is nth derivative of this one, that is 1, right? So a is equal 0, therefore x to the power n over n factorial, right? So this is something you studied, right? If you substitute n equals 0, 1, n equal 1, it is x squared over 2 factorial x cube over 3 factorial. So like that, it will go till infinity, right? Okay. So you remember you studied something, the value of E 2.78 something, right? So how we calculate that value? Using finite Taylor series only, right? So for example, x equal 1, if we substitute x equal 1, you will get E, right? E equal 1 plus 1 plus. So x equal 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial. So like that, it will go till infinity, right? So if you calculate this value, you can get the value of E, right? Okay, so this is the way we are calculating the E, right? Okay, this is something you studied already, right? In your mathematics, right? So what you are going to discuss this one, the second one, we are going to generalize this one for any number of variable function, right? So for that, I'm not going to discuss for higher order functions. Just discuss here the two variable function, right? Two variable function. The multivariable function also same. You can use this approach, right? The mechanism I am explaining, it will be same for all the cases, right? For example, let's say if it is multivariable function, sorry, two variable function, it is the function is x comma y, right? So in this case, what is the final that mean Taylor series expression is n equals 0 to infinity, same 1 over n factorial. Here you have to write the nth derivative, right? So in the nth derivative here, two variable function, therefore you have to differentiate each uh, variable separately, right? Like our chain rule, right? The same chain rule we will apply here. That means x minus a here dou x plus y minus b here dou y to the power n. Why n? Because I'm considering the nth derivative, right? So what is this actually? This is my nth derivative of function x comma y, right? Okay, right? So it's similar to like that. You can consider, right? Then f of a comma b, right? Okay. So this is your this one, right? Okay. Okay, let me erase this, right? It's similar to like that. You can consider, right? Okay. Uh, right. What is actually happening? As I told earlier, similarly here, so we have the function. This is the two variable function. X and y is the variable. This is your function, right? X comma y. So let's say in this case we have a surface, right? It is a surface, right? Okay. What is actually happening here? So you know the value of the function at one point, right? At this point, you know the value a comma b. A comma b, you know the function value f a comma b. This value you know. If you know this value, you are going to find the function value in from some distance from here, right? So this distance, it's a vector, right? Yeah, let's say delta r. That's what we are going to study here, right? Okay, right. Okay, so let me expand this term, right? So let me expand for first three term, right? So for example, n equals 0. So what is the n equals 0? The term is initial term t naught. What is t naught? N equals 0, this will be 1 because 0 factorial is 1. This is n equals 0, therefore this entire expression is gone. That will be 1. Only f of a comma b remains, right? So this is our initial point, the point you know here, right? So then n equal 1. So that is your first term, right? Okay, constant. This is the constant term. This is the first order term, right? The first order term, this will be 1 here, 1 over 1. So this is also 1. So therefore, just bracket. Then f of a comma b is outside. Just simple elimination of the bracket, right? F of a comma b, you can take it inside the bracket. So it will be x minus a dou x f of a comma b plus dou y, sorry, y minus b. So dou y f of a comma b, right? Okay. So this is your first term, right? Okay. So that means differentiate with respect to x, then calculate that differentiation at a comma b. Differentiate with respect to y, they calculate the differentiate derivative at a comma y, a comma b, right? So that is your t1 term, right? So let's say n equal 2. So that means t2. So when you substitute n equal to the second order term, 1 over 2 factorial is 2. So this will be x minus a dou x plus y minus b dou y. This will be squared here f of a comma b, right? Okay, so let me write it this one further. I will keep half here. So you can, this is just a expansion, right? A squared, a plus b whole squared, right? So first squared, x minus a squared. So dou 2 over dou x squared. Then I can take f of a comma b inside, right? Okay, plus. Now it's the second derivative, right? Here, 2 times 2 into x minus a, y minus b, dou 2, dou x, dou y, f of a comma b, right? Okay, plus y minus b squared dou 2 dou y squared f of a comma b, right? Okay, so now we find first three terms, right? So now how can you write the total expansion? T naught plus T1 plus T2. If you want, you can find, right? T3 until infinity, right? So this is our uh, uh, Taylor series for two variable function, right? Okay, so in most of the cases, we don't go uh, uh, more than the third, that mean second order terms, right? Because we deal with we develop the model in continuum mechanics. We assume like the material is continuum, so therefore between 2 points. Then mean if you go high order terms, then when you go to the small infinitesimal distance, that means the high orders you can ignore, right? It will be close to zero, right? Okay, right. So let me stop at this point in this video. It is very important video. Uh, Again, if you have any questions, let me know in the comment sections. I will try to include those part in our next videos. So again, as usual, if you don't subscribe my channel, uh, subscribe and share with among your friend circle. Um, yeah, see you in next video, right?